Good afternoon. I'm Spot On Weather meteorologist Matthew Euler. Welcome to the How the Weather Works training series. Today we're going to cover part 14A, which is going to be on the climate. Now the climate is very interesting. Let me just break this down for you. Weather is what you get, and climate is what you expect. And there's a lot of different landscapes created by weather over a longer period of time. The climate of an area. As you can see in this opening slide, there's a variety of landscapes. If we look at the image here on the left, we're looking at an area that's fairly wet and fairly green too. You see some of that vegetation. Looking at this particular area, looks more like more of a forested area. Then we have a desert with very dry earth. And then we have an ocean environment, an Arctic environment, and another ocean environment. So there's a lot of different landscapes. This one on the far right just shows fields that are green, perhaps some type of crop. And the climate of each of these areas determines what type of vegetation can grow, how people live in general in these areas. So let's get right to today's training topic. This is How the Weather Works training series, part 14A. This is climate. All right. So first I want to talk about climate and society. I want to talk about how the climate impacts our society. It impacts our lives in many ways, to include our housing, where we decide to live, the clothes we wear each day, the shape of landscapes, as well as the vegetation of those landscapes. Agriculture, what type of crops that we grow in certain areas of the world. How we feel overall, and how we live, and where we decide to reside. Additionally, I find this part very interesting, bullet 2, when we talk about the construction of an area, of the buildings of an area, of houses in particular. It's highly dependent on the climate. For example, if I were traveling through an area and noticed steeply sloped roofs versus flatter roofs, that would be an indicator perhaps of how much snow that area gets. If I look at an area that has steeply sloped roofs, that generally indicates that climate of the area, they tend to get more snowfall because snow is heavier, and with a steeply sloped roof, that allows that snow to kind of move off the rooftop more readily than, let's say, a flat roof, where that snow would accumulate and it would be very heavy and perhaps could cause that roof to cave through. The material of a house. What type of construction material do you notice in different parts of the world? That also is very important to determine as a determinant of the climate of an area. Additionally, we go way back in time in history, and before there was air conditioning and heating units, before there were HVAC systems, many of the local natives would build their houses or their huts with various material to act as a natural coolant, or to absorb heat in the wintertime to keep their little adobe warm. The location of trees in relation to the house, how these trees are planted, that has to do with climate. That has to do with how the sun moves throughout the course of a year in a particular location. And an example of that would be perhaps planting a tree on the western side of the house to kind of shade the house naturally from the more intense solar radiation in the afternoon hours. You have that nice effect of a tree there that's going to keep the house relatively cooler. We also decide where we want to live based on the climate, on that typical weather at a particular area. For example, we call Florida the Sunshine State. We also know that some folks like to move to either Florida or Arizona to avoid the colder climates. Some people have homes in locations further north in the summertime, and then they have homes in places like Florida and Arizona in the wintertime to avoid the colder weather. And then we base our recreational activities on climate. For example, you might know somebody who loves to go skiing. So somebody who goes skiing in the mountains, we're basically capitalizing on the climate, where an area that gets a lot of snow, and you get to go have fun, whether it be skiing or snowboarding in the mountains. Or maybe you heard of that term beach bum, And those are the folks that really love to live on the beach or maybe even go vacation to a city along the beach just to get that sun, to be able to go into the water and cool off. So again, climate has a major say. The long-term weather location or climate has a major say of how we live. Here are a couple great examples of how we deal with various weather regimes. And, we're generally used to what the normal is in our area, wherever we may live. So, example up here in the upper left, we have an image of a pretty significant snowstorm going on. And you'll notice people are dressed warmly. The climate, or the weather in this case, is determining what type of clothes they have in their closet. So perhaps on this day, they pulled out these heavy winter coats. And a lot of folks, since this is wind-driven snow, are using these umbrellas to kind of shield their face from getting pelted by the snow. The image here in the center top shows a lady. She's running through a heavy downpour. All right, but look at everybody and what they're deciding to do. What action are they taking to avoid getting drenched on, with these umbrellas all popped out? There's some people just walking. You can see some of the water is fairly deep, so there's a lot of ponding of this surface. And then there's a gentleman here who has no umbrella with glasses, and he's kind of like scurrying along, it looks like. The image in the upper right, again, goes back to that steeply sloped roof I mentioned. And a location like this with such a steeply sloped roof, to me, that would indicate this area most likely gets a lot of snowfall on an annual average. As that snow falls, it's going to more readily slide down this roof and not accumulate weight on the roof. Additionally, there's a lady here on the bottom left. She's bundled up. There's exceptionally cold weather. And so people, let's just compare different locations. People in Texas are not going to have the same type of clothes in their closet as people, let's say, in Minnesota. People in Minnesota know that in the wintertime it gets fairly cold, and they most likely are already going to have all this stuff in their closet, the hat, the heavy coat, the scarf, and so they're going to dress accordingly. Down here in the center bottom, we see the police department in the city generally spraying people. There's a hydrant here. You see a bunch of kids running through the water, just enjoying themselves, probably laughing, having a great time, getting wet on a hot summer day. All right. And then here on the bottom right, we see a gentleman skiing down a slope, having fun. This is the recreational activities. You go to the mountains, you get the snow, and many people know this already, and they pay attention to those ski reports each winter to determine when would be the best conditions for them to go ski or snowboard, stuff like that. So this is the many faces of weather, yes, and it's also tied in with the climate or the average weather at a particular location. And usually that climate period, we consider climate for the weather, it's usually over a 30-year period. Now let's jump into what exactly controls that average weather at a location. We call these climatic controls. And I'm going to cover each of these more in depth. We're going to start with latitude, which is a huge bearing on, for example, the temperature at specific locations across the Earth. The distribution of land and water, also a big consideration. The ocean currents, whether they be warm or cold, and their location in I guess reference to a coastal location, whether it's a warm or cold current offshore. The prevailing winds, whether they're onshore or offshore, predominant wind direction throughout the course of the year. The positions of the synoptic pressure systems, these high and low pressure systems. Mountain barriers, the location of mountains. Does somebody live in a mountainous area? What type of weather or climate is associated with the mountains? And then altitude, it kind of ties in with those mountain barriers. So let's first start off with the latitude. This is a big climatic control. In general, you have annual solar heating that each latitude receives. It generally decreases from lower to higher latitudes. It results in a general cooling of temperature toward the poles. Now, the seasonal changes in the amount of incoming solar radiation and the length of the day vary with the latitude. I'm going to show you some factors here in a minute on the next slide that go into that incoming solar radiation length of day. Tropical regions overall, they receive very little change. Their climate is pretty much hot and humid throughout the course of the year. The The polar regions, they tend to have more pronounced changes. And then one area I didn't put in here is the mid-latitude regions. The mid-latitudes, it depends on the season. Summer is hot, winter is colder, that type of thing. If you look at the bottom right-hand graphic here, I'm showing a general average temperatures across the world for the month of January. January being the winter season for the northern hemisphere up here. And you can see the further north you go, the colder the temperatures get, right? The further south you go, the warmer the temperatures get. And generally in this tropical belt, temperatures on average are higher than 70 degrees Fahrenheit throughout the entire course of the year. Not much change down here in the tropic belt. The mid-latitudes, again, that varies dependent on the time of year and the season. And then the higher latitudes, the North Pole and the Antarctic area, the South Pole, they're going to be much colder. Now, when we talk about intensity of sunshine, that's going to vary with latitude. There's 3 graphics on this slide that are very important to consider when we look at latitude, how far north or south of the equator you are. The first one here, the first graphic on the left, this shows you on the y-axis, the vertical axis shows you the insolation, incoming solar radiation in watts per square meter, ranging from 0 up to 600. On the x-axis, the horizontal axis, the bottom, shows the various months throughout the year. January, February, March, April, May, June, July, August, September, October, November, and December. And then I have different color lines on this graphic that show the various latitudes. Okay, so the blue line represents 0 degrees latitude, which is the equator. Now notice how flat this blue line is, right? The incoming solar radiation does not change all that much throughout the course of the year. See, it's above 400 watts per square meter on average, and then it kind of dips slightly below that in June and July, but then it kind of comes back around, back above it. So look how flat the blue line is for the incoming solar radiation at the equator. Now look at 30 degrees north. Notice how there's a difference here. The slope of this green line is becoming greater because we're going further north in latitude from the equator. And so in the January time period at 30 degrees north, my incoming solar radiation is just above 200 watts per square meter. When I get to the summer solstice time period in late June, now my incoming solar radiation in watts per square meter is approaching 500. And then as I go towards the autumnal equinox in September, and definitely towards the December winter solstice in late December, notice how the slope tends to go back down again for incoming solar radiation. So there's a more varying degree at 30 degrees latitude. Now at 60 degrees north latitude, that's the red line. See how even more highly or steeply sloped this red line is at 60 degrees latitude? Look at how low the incoming solar radiation is at 60 degrees north in January and February. It's below 100 watts per square meter. And then by the summer solstice, it's about 460 watts per square meter before nosediving again by December and the winter solstice in late December. It's back down very low once again, well under 100 watts per square meter. And then finally, the last line I wanted to show is the 90 degrees north line in incoming solar radiation. Look at this. From March to September, look where it peaks, above 500 watts per square meter. But look at the sharp rise from March to June, the summer solstice, and the deep dive all the way down again. You notice that there's no incoming solar radiation, let's say from late September through December on this side of the graph, right? And there's no incoming solar radiation from January to March. You want to know why? That is due to the fact that this part of the world at 90 degrees north of the North Pole has 6 months of daylight and 6 months of darkness. So you'll notice there's absolutely no incoming solar radiation at this latitude, basically between September and December and between January and March. And then you get 24 hours of daylight between March and September above the Arctic Circle. So real interesting stuff. Now look at the upper right-hand graphic here. I wanted to show the difference between a 90 degree solar altitude or solar angle versus a 45-degree solar angle. Now we call this the angle of incidence, the way the sun's rays are interacting with the Earth's surface. So this is the Earth's surface here in the horizontal. And this, when you have the sun directly overhead up here, above that 90-degree column, that means the solar radiation is shining direct, the solar angle, that solar radiation is very intense, very direct, shining right down on this particular area of Earth. And notice how much smaller this surface area is under that 90 degrees. Now if I tilt the sun to a 45-degree angle, the solar radiation to a 45-degree angle relationship to the Earth's surface, look how much more wider the radiation is in the overall column. And so the lower the sun angle, if I were to go down to a 30-degree sun angle, or solar altitude above the horizon, what happens is the incoming solar radiation is spread out. It reflects off air molecules as it moves from the sun towards the Earth's surface. There's a lot of reflection and scattering that occurs with that particular lower sun angle. So this angle of incidence, it varies dependent on the latitude. For a location generally in the tropics, it's closer to 90 degrees solar altitude for the sun, a 90 degrees intersection of the solar rays with the Earth's surface. So it's much more intense solar radiation in a very smaller surface area in the horizontal compared to, let's say this is the mid-latitudes at 45 degrees angle of incidence. And then if we were to go to the Arctic area, the sun may only be just barely above the horizon at certain times of the year. And then this column or that path the solar radiation travels, it's going to be much wider. So you're going to lose a lot more of that heating energy due to scattering and stuff like that. And reflection. Bottom right here, this shows the hours of day length. Now this is very important. As the sun moves in relation to the Earth, it revolves through the course of the year, there's varying degrees of daylight hours. Okay. Now at the winter solstice, generally what you have is the least amount of daylight hours in the northern hemisphere at the winter solstice. So you notice, it doesn't matter what we're talking about, this blue line representing the 70 north, or whether we're talking about this green line, or this red line, or the shallow line, 30 to 50 to 60 degrees north. You notice there's less than 12 hours of daylight in the northern hemisphere between January up to about March 1st. Once we get into March and closer to the spring equinox, or in late March, everywhere on Earth has 12 hours of daylight. The same thing over here at the autumnal equinox in late September. Every location on Earth has 12 hours of daylight and 12 hours of night, or darkness. Now, in the summertime, everywhere in the northern hemisphere has more than 12 hours of daylight. The further north you go, the longer the sun is out. So if you look at the very top of the graphic here, notice in this vertical axis over here, I'm showing the hours of day length from 0 all the way up to 24 hours of day length, or daylight. Look on the bottom here, this is the months of the year on the x-axis, the horizontal axis, and notice here at 70 degrees north, there is 24 hours of daylight, basically between, looks like middle May through about middle July. There's 24 hours of daylight. Notice at 60 degrees north, there is, let's see, that's 17, 18, 19, there's about 18 hours of daylight at 60 degrees north in the summer solstice time period in late June. And then all the way down to 30 north, we're at about 14 hours of daylight at the summer solstice. But then if you go to the winter solstice in late December, look at how the amount of daylight completely decreases below 12 hours. Additionally, note here, early January, from about 1 December through about mid-January, there's absolutely no daylight at 70 degrees north. There's nothing. See this blue line here representing 70 degrees north? There is no daylight here. So it's complete darkness for 24 hours a day during those specific times at 70 degrees north. So we factor this all in. Incoming solar radiation, how much of the sun's energy is intercepting the Earth's surface. We look at the angle at which the sun is above the horizon, very important. And then also we look at the hours of daylight throughout the course of a year based on latitude. The next climatic control I'd like to talk about is the distribution of land and water. Areas near larger bodies of water have less daily and seasonal temperature contrasts or changes as compared to locations away from the water. So if I were to look at an interior continental location, there would be a much greater daily and seasonal temperature contrast or change. Here are a couple of these bar graphs at the bottom right. I'm comparing two cities. I'm comparing San Francisco, California on the left to St. Louis, Missouri on the right. The red line, this generally will represent your temperature curve, okay? The blue bars indicate the average amount of precipitation. Now, this is delineated by each month equates to a specific number. For example, the 01 is January, 06 is June, the 12th month, of course, is December. Now, look at San Francisco. I want you just to pay attention to the red lines, these temperature lines. These are the average temperatures over the course of a year by each month for San Francisco, California. Now, notice your range in temperature throughout the course of the year is from about 50 degrees Fahrenheit on the far left in January up to about 63 degrees in September. Not a very large change, is it? From 50 up to 63, it's only a 13 degree Fahrenheit temperature change for the average temperatures in San Francisco because they are located along the right there along the California current, the cooler ocean current that goes down the coast of California. This keeps San Francisco a refrigerated city, really. It's a natural refrigerant or natural air conditioning. It's not very warm in San Francisco in the summertime, believe it or not. Look at St. Louis, Missouri, on the other hand. See how the red line, the temperature line, the average temperatures per month, how it is much more steeply sloped. St. Louis averages from about 34 degrees Fahrenheit in January for average high temperature up to about, let's see, that's even higher. It's up above 68 degrees Fahrenheit. I just want you to pay attention to the slope here. This is the most important piece. St. Louis is located in the interior continental location, whereas San Francisco is located along the water. And that ties in with the second climatic control, distribution of land versus water. So just wanted to point that out. Another climatic control, the third one we're going to talk about, is ocean currents. The oceans have a moderating influence on the overlying air mass. They're a major contributor to climate for specified locations. You typically see warm currents flowing along the east coast of continents and colder currents flowing along the west coast of continents. The prevailing winds, especially in the mid-latitude belt from 30 to 60 degrees north latitude, are generally from the west. We're in the westerly wind belt. So these westerly winds blow over these various ocean currents, whether they be cold or warm, and provide various temperature regimes and climate downwind of them. You typically find milder climates along the west coast and very warm climates along the east coast. If you look at this bottom right-hand graphic, it shows a circulation of the ocean. And let's just take a look at North America, for example, and we'll even move over to Europe a little bit here. All right, so we have these huge gyres. The ocean currents generally follow the shape of the gyres. We have an Eastern Pacific high-pressure system. We also have a Bermuda high-pressure system in the Atlantic. All right, so the general ocean currents flow around these huge high-pressure systems in a clockwise manner. Blue indicates colder ocean currents, which typically flow from the northern latitudes to the southern latitudes along the west coast of continents. An example of this would be the California current. And then the red coloring here indicate, and the arrows indicate the direction. The red arrows indicate warmer ocean currents. So, for example, along the east coast of the United States, we have the Gulf Stream current. In the western Pacific Ocean, we have the Kuroshio current. And these dynamic water or ocean currents, they are very dynamic in nature as far as the interaction with the overlying air. They can result in very sharp temperature contrast between the water surface and the overlying air, and result in explosive cyclogenesis or storm development. For example, we have a particular type of storm called a nor'easter that develops along the east coast of the United States and moves up off the coast of New England in the wintertime, because of the sharp contrast between the very cold continental polar or even Arctic air over the warmer Gulf Stream current. Additionally, these currents play a huge role in the steering of tropical weather systems and hurricanes as well. But in general, if you think about it, we have the westerly wind belt blowing across the United States. So the westerly winds blowing over a colder California current, that's going to give those locations such as San Francisco, California, a colder climate overall throughout the course of the year. Locations along the east coast of the United States, on the other hand, especially if you get an onshore wind, you're generally going to have very hot and sticky weather in the summertime. If the wind direction is from the northwest, from the land toward the water, you typically will get a colder, drier situation in the wintertime along the east coast. So these ocean currents are very important in how they interact with the overlying atmosphere. The next climatic control we'll talk about is those prevailing winds, which I kind of hinted at the last slide there. But in mid-latitude locations such as the United States, the prevailing wind is from the west. The resultant climate is generally cooler, as I mentioned previously, along the U.S. West Coast, because those winds, those westerly winds, are blowing over the colder ocean current, that California current. Now, when offshore winds occur across California, it's an entirely different type of temperature regime. When the winds blow offshore, that generally leads to a wind known as a Santa Ana, and that basically brings the wind over hotter, dry desert areas towards the coast. And also, those winds tend to move down the Santa Ana Mountains in Southern California. And as the air moves down any kind of higher elevation, it tends to heat and compress and results in very hot temperatures for Southern California. So that prevailing wind definitely makes a difference. That Santa Ana being an offshore wind, whereas an onshore wind across California, it's a major, major difference in temperatures. Continental interior location features more frequent air mass changes overall. There's a lot of weather disturbances and various frontal systems that move across interior locations. And then East Coast cities, the East Coast in general receives both warmer, humid air in the summer, where you get maritime tropical air and a more predominant southwesterly wind, and then colder, drier air from the northwesterly winds in the wintertime. Here's an example of the various cells that exist. The Hadley cell covers from 0 degrees latitude, the equator, to 30 degrees north latitude. And we have a subtropical high situated at 30 degrees north latitude. We typically have rising air motion, showers and thunderstorms closer to the equator. These are associated where the southeast and northeast trade winds meet or converge. This is known as an intertropical convergence zone. Okay, so generally we have northeasterly trade winds in the northern hemisphere. As air flows around the subtropical high in a clockwise manner, the Earth is spinning beneath it or rotating beneath these air currents. And then in the westerly wind belt, it occurs from 30 to 60 degrees latitude. We generally have westerly winds from the United States across Europe as well. The next climatic control we'll talk about are the position of highs and lows and what type of weather we typically see based on these positions of the pressure patterns. Now, the position of the polar front, the subtropical high pressure systems, as well as that ITCZ, the intertropical convergence zone where the trade winds converge, all these features generally move with the seasons. The ITCZ is generally farthest north during the northern hemisphere summer, and it's farthest south during the northern hemisphere winter. So the ITCZ kind of pivots both slightly north of the equator in the summer, northern hemisphere summer, to about 5 degrees or slightly south, 5 degrees latitude in the winter season. So there's a lot of areas, generally between 5 north and 5 degrees south latitude. They have rainy seasons and dry seasons. The rainy seasons occur in those locations where the ITCZ moves into the area. When the ITCZ moves away from that particular area, that's when they have their dry seasons. Now, the subtropical highs, as well as the polar front, are going to also move. They'll move farthest north in the summer season in the northern hemisphere. In the winter time in the northern hemisphere, the subtropical highs and that polar front move further south. The polar front jet stream is a major player in how it moves these particular high and low pressure systems in the mid-latitudes. That polar front jet will retreat to the north closer to that U.S.-Canadian border during the summertime, and then it will sink much further south in latitude during the wintertime. The next climatic control we'll talk about are mountain barriers. Now, these mountain barriers can alter air mass movement. You typically, if you're living near a mountainous area, you typically have wetter and cooler climate on the windward side of the mountain. As air rises, I'm showing you an example over here in the bottom right. You notice these arrows, how the air, when it can't just blow right through the mountain, so the air is forced to rise, and whenever the air rises in the atmosphere, it cools and condenses, forms clouds, and a lot of times it squeezes out the moisture in the form of precipitation on the windward side of mountains. Now, once all that precipitation is basically rained or snowed out, as the air sinks on the leeward side of the mountain, it tends to dry out, heat, and compress, and that results in what's known as a rain shadow effect on the lee side of mountains. So, lee side of mountains tend to be warmer and drier than the windward side of mountain ranges. And one other big note, as far as climate goes, cyclogenesis is favored on the lee side of the Rocky Mountains as an example. Sometimes these lows can spin up on the east side of the mountainous areas and then track basically to the northeast from there and can lead to a lot of heavy precipitation at times, especially during the wintertime. The next climatic control we'll talk about is altitude. Now, higher altitudes are generally going to be cooler than lower altitudes. You may have noticed, let's say you're traveling somewhere and it's hot where you're located, it's the summertime, but then you look in the distance and you see these snow-covered mountains, and you're wondering, how in the world are those mountains snow-covered? It's the summer. I'm sweating down here at sea level. How could that be? Well, altitude is the reason. The higher you go in the atmosphere, the cooler the temperatures get. Altitude also affects whether there will be rain or snow in a particular area. For example, if you're in a valley, temperatures are usually a little bit warmer during the day, and you see rain versus the mountains. You go higher up in the mountains in elevation, and you see snow. Day and night temperatures are also usually greater at higher altitudes, so that temperature range between morning and afternoon can be much more greater. You get less atmosphere at higher altitudes. That means there's less air molecules. They're less crowded up there, those molecules. During the day, it's easier for the sun's energy then to reach the surface and warm it. While during the night, there's less atmosphere for that particular energy to pass through. That means fewer greenhouse gases and effect, leading to a cooling ground. Here's an example of temperature and altitude, and I have covered this in a previous How the Weather Works training video when I talked about adiabatic cooling, adiabatic warming. But in general, if you were to launch a balloon with instrumentation, some type of thermometer, and you were able to track it on the ground with some sort of device, you would notice a general cooling trend with height as that balloon ascends in the atmosphere. Overall, let's talk now about global temperatures. We covered all the climatic controls. Let's start with looking at the hottest areas. Now, the hottest urban area in the United States is Yuma, Arizona. And if you're watching from Yuma right now, you're probably thinking, man, this guy's right on about this. The average high temperatures in July at Yuma, Arizona is 108 degrees Fahrenheit. Can you imagine that? And, after a while, your body just gets accustomed to these kind of temperatures. But I tell you, that would be a very hot climate to live in. In 1937 in Yuma, the high temperature reached 100 degrees Fahrenheit or more for 101 consecutive days. Now, the hottest place in the world is Dalal, Ethiopia. Now, in Dalal, it's generally located south of the Red Sea, near about 12 degrees north latitude. From 1960 to 1966, the average daily high temperature exceeded 100 degrees Fahrenheit every month of the year, except December and January. Oh, and that was a real treat. That was a real cool treat, right? In December and January, the high temperature of that time period reached 98 and 97 degrees Fahrenheit. So you're talking about a 2 to 3 degree Fahrenheit cool down. Not much of one. The average annual temperature in Dalal, Ethiopia, over that 6-year period was an astounding 94 degrees Fahrenheit. Woo! And you look at the graphic here in the bottom right, showing a typical desert landscape, an area that's hot and dry on Earth. We're very familiar with cacti. If you've driven through the desert southwest of the United States, you'll see a lot of these. Very parched landscape overall, too. Now, let's shift gears and talk about the coldest spots, generally in the U.S. and in the North America. Let's take a look at this. One of the coldest spots in the United States is International Falls, Minnesota. They are known as the icebox of America, this particular city. And why? The average temperature in January is just 3 degrees above zero. 3 degrees. In Minneapolis, St. Paul, this is one of the coldest urban or city areas in the nation, with an average temperature of just 16 degrees Fahrenheit for the 3 winter months of December, January, and February. And the record for the longest duration cold would go to Langdon, North Dakota, where the thermometer remained below zero for 41 consecutive days during the winter of 1936. Just amazing stuff. The coldest area, by the way, in North America, if we go up north to our friends up in Canada, generally found in Yukon and the Northwest Territories of Canada. A Resolute, Canada, has an average temperature of negative 26 degrees Fahrenheit in January. That's an average temperature. That's not even the wind chill. As far as around the rest of the world, and this picture really makes me laugh. I mean, this poor person here, this is like literally like ice freezing around the hood of his coat. If you look closely, you can see one eyeball looking through this, right? But this is all just instant freezing of ice around his hood of his coat. This is really impressive. All right, so the coldest winters in the Northern Hemisphere generally occur in the interior of Siberia and Greenland. Yakutsk, Siberia, has an average January temperature of negative 46 degrees Fahrenheit with a mean or average temp for the entire year at just 12 degrees Fahrenheit. IJsmit in Greenland has an average February temperature of negative 53 degrees Fahrenheit and a mean or annual temperature at negative 22 degrees Fahrenheit. I always used to think it's ironic that we call it Greenland, but yet it's so ice covered. And yet we have Iceland not that far from it, so kind of interesting. Now at the South Pole, you see some of the most extreme cold anywhere on Earth. At the Amundsen Scott Scientific Station, where they do a lot of research, the average July temperature, by the way, is negative 74 degrees Fahrenheit, with an annual mean or average temperature of negative 57 degrees Fahrenheit. Just astounding cold. Here is a sign there at the South Pole. Now, one of the things that's really interesting about the South Pole is it's elevated. So it's not just flat near sea level. That also adds to the fact, remember we talked about temperature and altitude, right? We say it gets colder with altitude. The higher you go in the atmosphere, the colder the temperatures get. Well, in the South Pole, they not only have latitude going for them as far as cold temperatures, they also have elevation. So here is a sign for the geographic South Pole, and the elevation at the geographic South Pole is 9,301 feet above sea level. So think about a mountainous area, going with altitude, being very cold, and on top of it, you're at 90 degrees south. So latitude and elevation or altitude here really producing these extremely cold temperatures of the South Pole. Interesting here, a little sign about how Roald Amundsen, his quote was, "So we arrived and we were able to plant our flag at the geographical South Pole." Of course, there's Robert P. Scott as well, back in 1912. And he said the pole, yes, but under very different circumstances from those expected. This is when all the explorers, there was a race to be the first one to the South Pole. There was a race to get to the North Pole first. That was the exploration time period. That was 1912 and 1911. As far as global precipitation goes for climate, generally what we see are equatorial regions, tropical areas are typically wet. The subtropics, which is around 30 degrees north and south latitude, and those polar regions, they're typically drier. I'll explain why here in a minute. Now, global precipitation is directly tied to the general circulation of the atmosphere, as well as mountain ranges. Now, this diagram to the right, I'm going to really delve into that now. This is really going to give you an explanation as to the distribution of global precipitation. So, generally, I have the latitudes marked at the top of this graphic. 0 degrees is associated with the equator. 30 degrees either side is associated with the subtropics. 60 degrees is where you typically get the polar front. And then you have the South Pole over in the far right, and then you have the North Pole on the far left. And so what we have, the overall general atmospheric circulation, that global circulation, we typically have a very heated area, very high solar angle throughout the course of the year in the equatorial areas. You get air to rise. This is associated with that intertropical convergence zone, or the ITCZ, where the trade winds converge. So converging air that rises at 30 degrees latitude now. So this air rises in the vertical in the troposphere, and then it spreads out at the top of the troposphere and heads toward 30 degrees south and 30 degrees north latitude. And what happens is the air ultimately then sinks at 30 degrees north and south latitude. So sinking air is associated with drier weather and associated with the subtropical high pressure. Now, once the air reaches the surface after it sinks at 30 degrees north and south latitude, it then flows along the Earth's surface towards 60 degrees latitude, and you have rising air motion again at 60 degrees latitude, at both the north and south latitude. Okay, and that's associated with the polar front. This is a case where you get the polar easterlies to converge with the mid-latitude westerlies, causing rising air motion and precipitation. And then, as the air flows in the upper troposphere, after rising at that 60 degrees north and south latitude point, the air then spreads out horizontally in the upper atmosphere before sinking again at 90 degrees north and south latitude at the north and south pole, and that is associated with dry conditions again with the polar high. So to summarize the global distribution of precipitation according to the climate, you would typically have a wetter climate around the equatorial areas between 0 degrees and 10 degrees north and south. You'd have a dry climate or high pressure at 30 degrees north and south. You'd have wet conditions year-round again at 60 degrees north and south. And then you'd have dry conditions again at the North and South Pole in the Arctic and Antarctic regions. Bottom line, this is sinking and rising air locations based on latitude across the globe in accordance with the global circulation. And then, again, just emphasizing this bullet, you get abundant precipitation to occur where air rises, and it's least abundant precipitation where air sinks. So in tropical regions, the trade winds are going to converge. You have the northeast trade winds from the northern hemisphere converging with the southeast trade winds from the southern hemisphere. Those two wind belts converge along what's known as the ITCZ, the Intertropical Convergence Zone. This produces rising air motion, towering cumulus clouds, and heavy precipitation all year long. Now remember, again, that ITCZ kind of follows the sun. So in the northern hemisphere summer, the ITCZ can range between 5 and 10 degrees north latitude. In the winter time in the northern hemisphere, the ITCZ sags south of the equator. And also another important point about the ITCZ is you can get these clusters of thunderstorms to develop from it and actually spin off into tropical cyclones. Poleward of 30 degrees north latitude, generally you have sinking air motion. This is associated with the subtropical highs. That generally produces a dry belt around the globe. It's no coincidence that the Sahara Desert of North Africa is in this particular region, where the air is sinking and drying out. Due to the pressure system shifting with the seasons, and generally northward in July and southward in January, the area between those rainy tropics and dry subtropics is influenced by the ITCZ and the subtropical high position. Now, in the colder air of the polar regions, there's very little moisture to work with in the atmosphere. Think about this. Colder air is much drier. It has a lower capacity to hold moisture as compared to warm air. So there's very scarce amounts of atmospheric moisture available in the polar areas. Winter storms, when they do occur, tend to drop light, powdery snow. And, your image or picture in your mind of an area like the Arctic or North Pole or South Pole, you're generally thinking snow-covered, right? Well, they don't get a lot of it from the sky, believe it or not, throughout the year. A lot of it doesn't fall from the sky. A lot of it just stays on the ground throughout the course of the year. In summer in the polar regions, on the other hand, you get a ridge of high pressure that typically tends to block storm systems, resulting in dry conditions again, even in the summertime in the polar areas. Precipitation, and we talked about in the mid-latitudes, the migrating position of the subtropical high has an effect on the west to east distribution of precip. Sinking air generally occurs on the eastern side of the subtropical high. This air tends to be more stable, drier, and cooler, and then you get colder upwelling water from the north, which cools the surface air even more, increasing the static stability. In summer, the Pacific subtropical high moves to a position centered off the California coast. This results in very strong and stable subsidence inversion, sinking air motion throughout a great vertical depth of the atmosphere above the coastal regions. And this results in that dry California summer. This bottom graphic here, I just wanted to show the various sides of these subtropical highs over the oceans. Typically on the eastern side of the subtropical high, you typically have stable air and sinking air motion, and colder ocean currents, by the way, beneath this. And then on the back side, the western side of these subtropical highs, you have rising unstable air and a much different situation, more moist conditions. And here is more information on the western side of the subtropical high. The air tends to be less stable, warmer, and moist. Now in summer over the North Atlantic, the Bermuda High, this is the main feature that controls the weather in the eastern U.S. in summer. The clockwise flow of winds around this high bring in southerly winds predominantly throughout the course of the summer season. So that's that moist tropical air coming northward from the Gulf of Mexico into the eastern two-thirds of the United States. So sticky, hot days is due to the circulation around this Bermuda High, maritime tropical air masses. This results in muggy air and greater instability, and often along the eastern U.S., due to this air mass being in place, maritime tropical air mass, you get afternoon showers and thunderstorms. In winter, the subtropical North Pacific High tends to move further south and allows storms to travel across the ocean, that Pacific Ocean, to penetrate the western states. It tends to bring much needed precipitation to California after a dry summer. The Bermuda High on the Atlantic side also is going to move south in the winter. This allows for storms to develop and travel eastward, frequently dumping heavy precip all the way to the east coast. Heaviest precip is usually concentrated in the eastern U.S. During the winter as moisture from the Gulf of Mexico gets pulled into an extratropical cyclone, and that moisture tends to move northward ahead of the storm system. These are some of the effects of nor'easters. Look at how high these waves are crashing onto this particular property, this house. This is from one of the bigger nor'easters that occurred. Here's a satellite image of what a nor'easter looks like. This was January of 2018. This was one heck of a storm from the mid-Atlantic northward to New England, producing heavy amounts of snowfall. Okay, now let's take a look at mountain ranges and precipitation a little more closely. Mountain ranges tend to disrupt the idealized pattern of global precipitation. Mountains tend to promote convection, or that rising air motion on the windward side. The heated slopes in the summertime of the mountains generally forces the air to rise along their windward slopes. That's due to what's known as orographic lifting. Windward sides of mountains tend to be wetter than the leeward side. So if you're ever looking at property and you're going to buy property, definitely want to pay attention if you're in a mountainous area, what side of the mountain that property's on. Is it on the windward side or is it on the leeward side? If it's on the windward side of that property, guess what? You're probably going to have cooler and wetter conditions throughout the course of the year. If you're on the leeward side of that mountain and living over there, you're going to have much drier and warmer temperatures on the leeward side. And that will lead into, as far as the cost of cooling and heating these homes as well. Now, Northwest Washington State, this has a major rain shadow effect. There's over 150 inches of precip on the windward side of the Olympic Mountains. And then you just travel east a little bit, and there's only 17 inches of annual precipitation on the leeward side of the same Olympic Mountains. So that tells you how mountain ranges and precipitation go hand in hand. All right, that wraps up the training today. Part 14A, how the weather works. This is on climate. I'm working on 14B now, and I'll go more into the different type of climate systems, for example, the Köppen climate system. Just generally showing you the types, the classifications of climate around the world. In general, I also have a higher latitude training put together. Most likely I'll make that part 15, but I'm working through the series here, the How the Weather Works training series. I hope you have enjoyed all these videos I put together and just explaining the weather and climate as a whole. And looking forward to future training, and again, looking forward to providing the latest up-to-date forecast from Spot On Weather as we head towards the fall season and the winter ahead. Should be interesting. All right, everybody, that's all I've got for now. Until next time, take care and God bless everyone.